present is Andrés Sambarino from Sorbonne, and he will talk about the cone of Jordan variations and applications.
Hello, do you hear me? This is fine, yes? Cool. Nice. So thank you for the invitation. It's great to be here. So let me begin by introducing some notation. So let's consider some D times D matrix, right? And so let me denote, let me consider its eigenvalues, or essentially the diagonal matrix in its Jordan decomposition. And I'm going to order these diagonal entries in decreasing modulus. So essentially the lambda I are what? Are then the logarithm of the eigenvalues of the modulus. Of the eigenvalues of G with multiplicity. So I'm putting them in decreasing order. So I'm going to consider now the vector lambda of G, say. This is now the vector of the lambda I. And we can consider this as a function, actually, from G to, so I'm considering the determinant 1 matrices. So now I'm taking the logarithm of the modulus. So these numbers add up to 0, but they are ordered. So this space is usually denoted by like an A plus. So essentially, A is D numbers that sum 0. And this cone inside A plus is just D numbers of, so an element of A, but ordered. D numbers of some 0, but the first one is bigger than the second, and so on. So this map, this is a map, it's a differentiable map, and it's called the Jordan projection. So let me call this G. Just the eigenvalues of G. So now we have not one element, but a group. And we consider something, we can think of this finitely generated group, but it's not going to be so important. But we have some morphism to G. And now for each element in G, we're going to have now its vector of eigenvalues. Right? So we're going to build up an object using all these vectors. And this is what? So essentially, let me just draw here. This is A plus. So this is the case, the three-dimensional case. So now for each gamma in my group, I'm going to have some vector lying here. What I'm going to do is consider not the vector, but the half line it determines. Okay? And I take all these lines, these half lines, and I take the closure of them. And this, we give a name to this. So this is called Benoit's cone. So what is this Benoit cone? Let me call it L of rho. So this is what? This is essentially take the union for gamma and gamma. The half line determined by this, the vector of eigenvalues, and then I take the closure. Okay. So it's the first time in this conference that this object appears. and it's Thursday afternoon. So maybe I will spend some time explaining what this is, giving you some hint. So the key result here is a theorem of Benoit. So it has like two parts. So the first part, so let me assume, of course, that rho of gamma, so assume, is Zariski dense. So essentially, rho of gamma is not contained in any Lie subgroup of SLD. Then what happens? Then this cone is going to be convex. It's going to be a convex cone, and it will have non-empty interior. So this is the first statement, and the second one is not about the cone, but it's something that came a bit later, and actually some sense a stronger result, which is the following. If you look at the group spanned by all these vectors, the additive group they span is dense in A. So essentially the first statement is saying that there cannot be any relation between the eigenvalues of gamma other than the relations that are forced for being in G, because the gamma is in G. Right? It's the only. And the second statement is a stronger way of saying that. There's no arithmetic relation even between them. Okay? Yes. So yeah. So now I forget about the lines. I consider again the vectors, and I look at the group they span, the additive group they span, and essentially this is dense. So it's a stronger way of saying that the cone has an empty interior. This implies. So if you know, for example, the cone is convex, then the second statement implies a non-empty interior already. And convex is actually kind of easy. So let me give you two examples of how this applies, rather quick examples, because I think this is a very natural theorem. The first time I saw it, it seems like it's natural. What else? But so it took me a lot of time to understand that this is a very deep result. So let me give you just two very simple examples of consequences. So the first one is really easy. So just to give you an idea of what's going on. So consider gamma a subgroup of SL3R, right? And assume it acts irreducibly on R3, so that doesn't preserve any subspace. Okay. And so assume, for example, that for some magical reason, each gamma preserves some quadratic form. And the conclusion will be that there is a quadratic form preserved by all gamma. Maybe non-degenerate, if you want. Then there exists a quadratic form preserved by every gamma. By gamma. So this is the typical, one of the typical applications that you can have from this kind of result. So the proof is very quick. Like if you preserve a quadratic form, this gives you a condition on the eigenvalues, right? The top has to be the inverse of the bottom, right? So they all lie in a particular line. So the cone cannot have interior. So it's not Zariski dense. If it's not Zariski dense, you're in a subgroup, and there are not many subgroups of SL3. That's kind of easy to compute. And that's done, and that's the proof. If you want to play this in bigger SLDs, then, well, you got to study subgroup of SLDs, and this is, the bigger the D, the harder it gets, right? But actually, the most important, I guess, consequence of this, again, a non-empty interior, is something that is called market length spectrum, rigidity. So now you consider two, so you have the same group, but you represent it in different SLN. You could have the same, but you consider two representations. And you assume, for example, this is just an example, assume, for example, that for every gamma, when I look at the spectral radius on one representation, I get the same spectral radius than on the second representation. This would be a market length. So we can fix one. So we fix lambda 1, the top eigenvalue, say, and we can consider this to be some sort of length of the curve. And if all this, if you have a coincidence in the length spectrum market, so for every curve you have the same spectral radius, then the conclusion is that there exists an isomorphism. So in particular, k equal d, right? Sorry, I have to assume Zariski dense both of them. So they are both Zariski dense. And the conclusion is, of course, that n equal, so d equal n equal k, and you get an isomorphism when you projectivize. Intertwining the reps. So they are the same. And so here the important thing is that you're not going to prove a theorem. So this doesn't follow from the theorem that I wrote here, but you have to generalize this statement not to SLNR, but to products of SLNs. So follows. Generalizing to products. Meaning to any semi-simple Lie group. And I guess the point that I want to make in this, by doing this way, is that when you generalize to products, actually the proof is exactly the same as the proof for SLN. So if you understand the proof for SLN and you know some Lie theory, then the same proof gives you the statement for products. And so this really is a consequence of this market length spectrum is really a consequence of the theorem, of Benoit's theorem over there. So what I've been trying to do, which is related to this, is to consider some variation of this picture. So instead now instead of having a group, so let me denote X. Let me consider the character variety. So the space of morphisms from gamma to G up to conjugation by G. So essentially, Benoit's theorem is about a point here, And I want to replace this point by a tangent vector. So let me introduce some more notation. So now I have my gamma and gamma. And I'm going to consider, this gives me a function on the character variety, essentially like this. It gives me a function, which I'm going to denote like this. And so this is just a lambda gamma of rho is rho, is of course lambda of rho of gamma. And at V, then what I'm going to consider is the differential of this map at V. This is the object that I want to study now. So what's happening? What is the picture to have in mind? I have my cone. I have all these points. And now above each of these points, I have a small arrow. Small or big, I don't know. So essentially, the point is just lambda gamma of rho, and the arrow is just literally the derivative in t equals 0 of lambda gamma of rho t, if the derivative of rho t is v. And now I'm gonna do the same thing. I'm going to consider a cone built out of these directions. And the idea, of course, should be that there is no relation between all these directions. Right? But you can, like, when you move your representation a bit, your morphism, you move your group a little bit. And the idea is to show that, I mean, a priori they could all lie in some subspace, right? They all have the same variation in the same directions. And that's the idea is that this cannot happen, right, which is expected. So I guess the theorem, I can write it like this. So assume, so let me, the hypothesis, so rho of gamma is Zariski dense. And assume there exists some gamma which is loxodromic. So I didn't say what it is. So let me say that gamma, so rho of gamma loxodromic if all the inequalities are strict. So assume there is some loxodromic element such that along my curve, its eigenvalues move, right? So, of course, if you move your representation by conjugating, none of the eigenvalues is going to move, right? So then that's the trivial vector in the character variety, right? So this is what you don't want to consider. You want to consider a vector which is not zero in the character variety here. Such that d lambda gamma of v is not zero. So then what is the result?
You're taking the derivative at rho, right?
Yes. Yes. Where do I have to write this down here? Yes. Yeah. Here too, or here. Yes. And so the result is, of course, that you do the same thing. You do the union of gamma, and you look at the directions, the half directions given by these derivatives. You take the closure, you give this a name, and you call it the cone of Jordan variations. that depends on V. And the result is that this is convex, again, it's convex, and has a non-empty interior. So I guess this could be like the first statement. And so it says essentially what we expect. There cannot be any relation between these derivatives other than the relations that are forced by being inside the group G. Yes. So then you can try to do some refinements. So the point is that as opposed to the Benoit cone, this is likely to be like all around. It's likely to be everything all the time. I mean, not all the time, but it seems pretty reasonable that this is everything because of convexity. Because nothing is forcing you the direction should be anywhere a priori. So it's natural to consider some refinements of this, which we're not going to use later, but I just want to advertise them because I like them. And so this statement is saying in some sense that, yeah, there is no relation between these derivatives, these directions. Now you want to do something better, right? Like like this density theorem, which is a stronger form of independence, some sort of non-hermeticity. But here there's another point that appears, which is the base point, rho. And the result is that there is no relation, not only among them, but also with respect to the base point. So essentially, when you look at the pairs, which are, essentially vector of eigenvalues and their variation, this is a pair. All these guys, they span a dense group. Span a dense group. Of now A times A. So this is some sort of base point independence or something like that. Maybe just write the name. Okay. And so this gives you the possibility of defining a new object, which is going to depend on some length function. Like in the other case, we picked lambda 1, like the top eigenvalue, but you can pick any function. So if you pick any function, sorry, you're going to pick a linear combination of eigenvalues that is positive on the limit cone. So this is going to give me some notion of length. Then what I'm going to do, I'm going to normalize. Instead of considering directions, I'm going to, for each of these directions, I'm going to pick one element, one particular element of this line, this half line, and it's going to be related to this. And it's going to be this length. And now you look at the set. You take the closure, and you give a name to this. Maybe you don't, because we're not going to use it. But the point is that this, what you get now, you get a compact, a convex, non-empty interior set. So for example, I think this is new. Maybe someone here can correct me. But for example, right? So when you take d equal 2, so it's a 2. Or PSL2, because this doesn't really depend on the thing. So what I'm doing is, for example, consider a point of time mirror space, and you consider a tangent vector of this point of time mirror space. So yeah, maybe you can write that down. Consider some point on the touch mirror space of your surface. And so for the Jordan projection, now is going to be the length for the associated metric. And this derivative, then this derivative is going to be the derivative of this length when I move the metric, right? And this spans a dense group of R2. So something that we did before, actually. So with Martin, Dick, and Francois, essentially it's a bit weaker than this. This is 13, I think. It's not contained on, it's not at, what did we prove? It's not contained on a line. So this group not contained on a line, which is a bit weaker than just being dense, in R2. So if you try to, if you extend, so the result I stated for SLD, you can generalize to other semi-simple Lie groups. You got to be a bit careful, especially for the second parts. But for SLD, this is correct, everything that I wrote. And so now you can consider not only one hyperbolic surface, but many that are different, and different vectors tangent to each of these hyperbolic surfaces. And all the variations that you're going to get, they're going to span a dense group of this R to the number of surfaces you picked times 2. So there's not going to be any relation between all the variations of length for these different metrics. So, but the actual reason I'm thinking about this, so the main motivation for me so let me just put a title, say, is to understand house of dimension degenerations. So what are we talking about? So let me just begin with a broad framework, and then I try to specify until I get to what I want to say. And so essentially, the main framework will be the following. So you have your SLDR that you're going to consider now inside the complex SLD first. And you pick some Grassmannian. So you pick some number. Sorry. So pick some Grassmannian of RD. And now this is naturally sitting inside here. Now I have my group. I had my group before, so I have my row here. And so it turns out that on each of these Grassmannian, in each of these Rosmanians, my group is going to have a limit set. In the same way it has a limit set on the visual boundary of H3, here the same game is going to play, similar game is going to play for each of the Grassmannians. So you have one limit set in the projective space, one limit set in the two-dimensional spaces, and also in the combination of them, in incomplete flags. But let me just restrict to this case. So I'm going to have here some limit set. So let me just say that this is well defined in many cases, in particular if rho is Rayleigh dense. And so what is the picture that I want to have in mind? So here I have my real Grassmannian. And so this would be this. And here now having the big ball would be the complex. And here I have my limit set. I don't know what it is. Maybe fractal a priori. I'm not making any particular assumption, so it could be kind of anything. But the idea that what I want to explore is what happens with this limit set when I deform my representation to the complex group. Right? So essentially, the idea is you deform rho to have values to be Rayleigh dense, maybe. In the complex characters, in the complex group, sorry, and understand the half of dimension of this limit set. How does it vary? How does it move? What happens? That's kind of the main framework for what follows. I mean, so of course, in this generality, the answer is I cannot say anything at all. This is understanding the half dimension of limit set when d is bigger than 2. It's a very difficult problem, especially because the dynamics on the Grassmannian is not conformal. You send a ball to an ellipse, and this really complicates trying to determine the half dimension using the group, the dynamics of the group. This is really difficult. But the case we're going to restrict is doable, is tractable. So what is this case? So this is a particular case, but it's very important to me. So restrict to Hitchin representations. So what is this? So essentially, what did Hitchin prove? So Hitchin proved, I think it's in the 90s. So essentially, when you look at the character variety of the fundamental group of this surface, now I'm going to put a P, PSLDR. So I have this space. And so essentially, so it's a higher genus, right? Is genus greater than 2, closed, connected, everything. So what he proved is that he computed the number of connected components this space has. So I'm going to take d bigger than 3. And essentially, he said that this space has 3 connected components if d is odd, and 6 connected components if d is even. So these 6 connected components that appear is actually because when d is even, PSLD has an extra outer automorphism that gives you but that doesn't preserve the component. So it's like when D is even, you have these 3 and other 3 that you obtain by applying this outer automorphism of PSLDR. And so what happens? What happens is that let me draw the case D odd just for the cartoon. So you have like 3 components, and so inside PSLDR you have PSOD. The fundamental group is C2, and so essentially when you consider characters in this compact group, you have 2 components. And these are the components that I'm drawing here. Contain this. So these 2 components contain a rep with values in SOD. And the magic of the paper is that there is this 3rd component that appears over there, and nobody knows what this is. It's like it's some sort of a mystery component. Especially because when you look at the natural invariance, how do you write mystery? Yeah, thanks. So when you look at the natural invariance, you cannot distinguish this from the other 2. So this one are there naturally in some sense, and this is something that appears by kind of by magic. And so this is why this attracted a lot of attention, I guess, and a lot of work came on this. And so it turns out that this component, this mystery component that we call now the Hitchin component, is a ball, is homomorphic to a ball, so diffeomorphic to a ball of dimension, the Euler number of the surface minus the Euler number times the dimension of PSLD. And also, it has a natural copy inside. It has a natural copy inside of time mirror space. So the representations in this natural copy are called the function. So there's a lot of work about this. So I guess the main breakthrough is by Francois, showing that every element in this component, is discrete and faithful. And another thing that he did, essentially, is that now you're going to look at the limit sets. So this limit set that lives in the Grassmannian over D. It turns out, and this is something that at the beginning was certainly very mysterious, is that this is a C1 circle. So let me just add that for k bigger than 2, you need something else, not just what he did. Also, you need something we did with Bea and him. So now I go back to my picture. And I have here my Grassmannian, and I have my limit set in this case, and I know it's It's going to be a C1 curve. And so what I'm going to try to do, when I deform my representation now in the complex group, in the SLDC, inspired, of course, by Bowen's result or by Bridgman's result and by Mullen on the Hessian of the half of dimension when you deform a function inside a quasi-function space. So essentially, this should become some sort of fractal, and that's kind of the question. That I want to answer. So there is a recent paper by Biaggi, Pozzetti, and Farr. I think I said the names backwards. That says instead of looking at each Grassmannian, you look at the collection of all of them in the space of complete flags. Then this will be fractal, if your deformation is Zariski dense. But here I want to restrict to each Grassmannian. And so to each Grassmannian, we don't know what happens. So, but what I do know is how to compute not the half of dimension, but the second derivative. So the idea is that this is a C1 curve, and so when I move in the complex guide, this is a critical point actually. So the Hessian is well defined because the dimension has to be equal or higher because here is 1, and now it's a circle. It's still a circle though, so it's at least 1. So the point is that the Hessian of the half of dimension when I move in the complex group is going to be well defined, and this is what I want to understand and hope it's positive, so that at least I will get a local fractal behavior. So let me just state this in a precise way. So let me consider a tangent vector, but to Hitchin. So I'm going to consider special deformations. Let me draw a picture. So now this ball is not a Grassmannian, but this is now the Hitchin component. This small ball here. The big ball is going to be the character variety into the complex SLD. Right? And now we're going to have a vector. I'm going to have some rho here and some vector. And I'm going to apply J. I'm going to multiply by the complex multiplication, which comes from the fact that this is a complex group. So here I have my JV. And I'm going to study the formations along this JV. Right? So essentially what happens, so you have this result. The Hessian of the half of dimension function on the K Grassmannian at a JV is going to be 0. If and only if the cone of Jordan variations that we defined earlier is contained in the kernel of some particular function, which is called the K simple root. So this is not new. You need a lot of work to get this equivalence. In particular, so let me just say some names of the works that you need. So you certainly need BCLS, and then you need a paper by Rafael Potri and myself. And then you need a more recent paper by Bridgman, Pozzetti, myself, and Anavina. So yeah, this is not obvious. And you also need this result over there. So this is the point. So I have my V, which is tangent to the Hitching component, okay? And I'm going to deform GV. I'm going to deform in the direction of JV, sorry. Okay, and what I'm saying is, when I move in this direction, the Hessian of the half of dimension is going to be 0. So essentially, no infinitesimal deformation, no infinitesimal fractal behavior. If and only if, when I look at the cone of Jordan variations on V, it is contained on a particular subspace. And so the main theorem was saying that this didn't happen, at least when rho was Zariski dense. So let me just add this here. So if rho is Zariski dense in the Hitching component, so if rho S is Zariski dense and BSLDR, then you're good. Then your Hessian that you wanted to compute is positive, and you have some sort of local Bowen result in particular. What is more interesting, what was surprisingly interesting, and it's something that has obsessed me for some time, and I think it will obsess me for still some years, is what happens along the function. So what happens if rho is not Zariski dense? No, because the base point is Hitching, right? I'm standing on a Hitching point, and I'm taking a tangent vector to the Hitching. And then I'm deforming along the JV, okay? But the point lies in the Hitching. So it is contained in PSLDR. So the assumption is it's not contained in any subgroup of PSLDR. That's the assumption. So yeah, if Hitching, if the base point, you're in the Hitching, is generic, then when you deform in the Grassmannian, the demi-set in the Grassmannian is going to grow after you deform, not at the beginning. The problem is what happens along the function, or when it's not Zariski dense. So essentially, so Guichard in 2012, classified Zariski closures, possible Zariski closures of a Hitching representation. So essentially, there is an intermediate case. I'm not going to state the result, but essentially what happens, the intermediate cases, you can kind of work them out, and they are easy to understand. And the hardest situation to understand is the function case, is the function points. So this guy's here. So we have we had our mystery component, and I told you that it naturally contained a copy of that mirror space. And these points here, because of the symmetric closure is an SL2, they are the hardest to understand regarding this problem, and this is what I want to finish with this. Just give you a hint of why this is hard, why is this strange. So what happens, let me, so let me give you an example. Maybe not examples, but let me tell you what I know. So for example, yes, maybe just an example. Consider the first Grassmann. No, maybe sorry. Maybe I write it like this. So what happens is the following. There exists, so for every k, there exists a Diophantine equation on two variables, d and e. So let me call it p. On two variables, d is the d of SLD, and e is some other parameter that I don't have time to explain, maybe later. Such that the Hessian, so that for every functional representation, the Hessian of the height of dimension at JV is going to be 0 if and only if this equation is verified. This equation over the integers has to be verified. And this is kind of what's going on. This is maybe a mysterious way to do it. So, but the equation is explicit, but very difficult to understand. So let me tell you what this gives you. So for example, when k equals 1, then I don't remember the equation, but it's very easy to see that it always works. So essentially, this guy that you want to know is good. So the projective space behaves nice. We have a local Bowen theorem for every d in the projective space. So this is k equal 1. Then you go to k equal 2. And then you get an equation which is easy to solve. And essentially what happens is that this is going to be 0 if and only if d equals 4 or 7 or 11 or 16. So the way to remember the sequence, but this is just a mnemotechnical rule, is like you look in the plane and you take away E lines in general position, and you look at the connected components that you have, and that's going to give you your D. So for example, if you take two lines, you have 4 components. If you take another line, you have 7. If you take another line, you have 11, and so on. And this is going to give you your Ds. But this is really doable. This case is particularly easy. What is more interesting is this case. And here you get something which is stranger, more appealing in some sense. So you're going to have some degenerations along the function if and only if you're in SL6, or you're in SL17, or you're in SL58. And these are the only ones. So what happens in this case is that what happens in this case is that when you look at this equation, so what happens here, so in this case, what happens here is that, so maybe I can write you the formula. I don't think if I, well, that doesn't matter, but the point is that this equation, when you look at the complex solutions over C, you get a genus 1 curve. So essentially, this is an elliptic curve, and it turns out that elliptic curves, the different equations that give you elliptic curves can be solved over Z. So there exists a method called the elliptic logarithm method that essentially gives you a recipe to solve your equation over the integers. It's pretty painful, huh? I was talking to this colleague, and he suggested something like this. And he told me that there is some method, something like that, but I'm not sure it's worth it for solving one equation, you know. But I really wanted to do it. And when the thing is k equal 4, I don't know. I don't know what happens. There's probably finitely many solutions. And that's the mystery. So that what happens in the k equal 4 case is that when you go to this equation, you get a higher genus curve. And apparently, there's no method to do something like that. Seems like an untractable problem. Yes, maybe I'll stop here. Thanks.